Yeah, I've learned to wait for the recording in progress message and to not speak straight away. But thank you very much for the invitation, and thanks everyone for coming to the talk. So this is a project that we've done with Astrid and Benjamin when I was in Heidelberg before summer of 2025, and so this was published on Archive in October of the same year, and this is a work about trying to constrain couplings between ultralight dark matter scalar candidates and the standard model or parts of the standard model, and to try to make these constraints coming from the quantum gravity. Maybe I click my slides. Oops. Okay, so first I introduced dark matter, which I'm not an expert on, but I've had a lot of reading. I've done a lot of reading, and I'm now very interested in it. So there's plenty of evidence for dark matter, as we know. Some of it is astrophysical or cosmological, and I think a nice way of seeing it, and one of the first, historically, one of the first pieces of evidence for dark matter was galaxy rotation curves. So as you can see on the right-hand side, there's two lines basically, which is one line is showing the expected velocity of rotation of the galaxy M33 without dark matter, and the observations actually fit the top line much better, which is basically positing the existence of some mass which does not interact electromagnetically or with other forces except gravity, essentially. And so this was one of the first evidences for dark matter. There's others. You have various types of evidence through gravitational lensing experiments or anisotropies in the cosmic microwave background. Also very pretty pictures. For example, the collision of galaxies, for example, the bullet cluster collision, which actually left a mass distribution which was very well explained by the presence of dark matter. So now we're particle physicists, and we say, well, what is it actually made of? And there's various things it could be made of. I mean, we have no idea, right? We have some candidates that we know of for matter particles, and we say, might it be a spin 2, a spin 0 particle, sorry, a fermion or gauge fields? And within these classes, there's obviously subclasses as well. So can it be a scalar or pseudoscalar? What spin does it have if it's a gauge particle, etc.? Very good. And so in this talk, I focus on the possibility that dark matter is actually made of a scalar or a pseudoscalar particle, which is one of the simplest cases you can consider. Now, what type of dark matter am I talking about specifically? Here, I'll be talking about ultralight dark matter, which is essentially simply dark matter with masses under 1 electron volt in this range of masses here. And for simplicity, I assume that all or most of dark matter that is in the universe is made up of this scalar dark matter candidate, which is ultralight. So I take literature values for various things. For example, experiments have ranges of values for the velocity of dark matter within the Milky Way, and also the energy density that it represents. And so these are standard literature values, which for cold dark matter means that the velocity is actually quite small compared to the speed of light, making it non-relativistic. Also, a very interesting thing you can look at for ultralight dark matter is the occupancy per de Broglie volume. So here I look at n, which is essentially a number density times lambda dB, which is lambda dB by itself is the de Broglie length, and lambda dB cubed is a de Broglie volume. And so actually the number occupancy is simply the energy density divided by the rest energy, which actually dominates because this is a non-relativistic thing. And then I multiply this by the de Broglie volume, which is just 1 over the mass times the velocity, and I cube it. So of course now you realize that actually because the mass is so small, it's in such a small mass range that essentially this is strictly larger than 1, and for very small masses reaches enormous numbers. So essentially there's a lot of the same dark matter scalar particles in a given de Broglie volume. This means that wave functions would overlap and that this has to be bosonic. But it also means that it's a very good approximation to consider this as a classical field. So essentially, ultralight dark matter can be taken for our experiments in the Milky Way and on Earth can be taken as a classically oscillating field. Essentially, this is a very good approximation. So I call it phi, some scalar field with a time dependence, and it has an amplitude and some oscillation frequency, which is essentially proportional to the mass. Here, ULDM is ultralight dark matter, and for the rest of the talk as well. Very good. So now, with a slightly strange title for this slide, how might you detect the presence of such a dark matter candidate, a scalar dark matter candidate? Some of the original ideas come from Donoghue and Damour, who in 2010 wrote down this type of Lagrangian from an EFT perspective, where essentially you have these D couplings, which stands for dilaton. It's mostly historical reasons why this is called dilaton couplings, but sure. This is coupled to gravity, and this is this dark matter candidate. And there's different dilaton couplings to different parts of standard model matter at this energy scale, where not all quarks are included and some are integrated out already. So very good. So, okay, one can write this Lagrangian down and make testable predictions and bound these dilaton couplings, DE, DG, etc. So one of the ways you can test this is, of course, that you're introducing a new long-range force through the scalar field. And so you can make tests through fifth force experiments, essentially, because you know that the scalar field will contribute some part of the Newtonian potential and will correct it in some way. And you can put stringent bounds on generally with these tests on such couplings. So that's one way. Another way would be violations of equivalence principle. So here you actually explicitly see that there's many couplings for very many different types of matter between the scalar and the standard model matter. And so this is exactly what is meant by breaking of the equivalence principle, in the sense that if you could measure the relative acceleration of two bodies which would be made of different types of matter, and there would be differences due to the force that the scalar field makes, you could bound essentially these couplings by doing this. So this is what people call composition dependent tests, in the sense that you might take relative accelerations between bodies made of different things, of different matter. And the third way, and the most, at least for today, most interesting way, is that the scalar field is going to induce oscillations of fundamental parameters by these couplings. Essentially, all of these couplings would enter and correct standard model values for, let's say, the fine structure constant or lambda QCD or the mass of some quarks. And these couplings would enter and correct these values and make them oscillate. So this is exactly what we're talking about. And as you remember, I just told you that ultralight dark matter is exactly doing this, because it's essentially a classically oscillating field. How can you detect this? I mean, this is the theoretical framework and the EFT idea, but how are you detecting this? First, I do a little introduction on how atomic clocks work, but essentially you can detect this through atomic clocks. So the idea of an atomic clock is simply that you take atoms and you shine a laser on it. And then you scan through the different frequencies that this laser can have. So these are the tiny blue dots on the curve. After scanning through various frequencies, you get some sort of point distribution, which you fit with a Gaussian or a Lorentzian or whatever distribution you like, which fits this. And this is called the line shape. And essentially, this will be peaked. This will have a width, of course, and this will be peaked at μ0, which is exactly the frequency of excitation from the ground state to the first excited state of electrons of the atom you're shining the laser onto. Very good. And in the end, how do you make an atomic clock? Well, it's essentially what I just said, which is that you scan over these frequencies and you try to tune your laser to have a frequency of exactly the resonant frequency which is used to excite your electrons. Then you count cycles of the laser signal, which has the correct frequency corresponding to a specific atom. Then you set the scale, and you say you have a clock. There you go. And this is actually how it works for seconds. So seconds are defined very, very precisely by computing or by setting this up for the hyperfine transitions in cesium atoms. And this is actually incredibly important for various things of day-to-day life, like GPS. Like if your GPS was not based on atomic clocks, errors to GPS locations would be enormous, sometimes kilometer errors. Very good. So what does this have to do with dark matter? Well, I told you that dark matter essentially is this, or ultralight dark matter can be approximated by this classically oscillating field, which would correct various things and also correct atomic properties. And by correcting atomic properties, it would change the resonant frequency of an atom by some amount. It would give it a time dependence, an oscillating time dependence, as I show. So it would be essentially this frequency would become the value it has with no dark matter present, plus some correction, which is proportional to the oscillating scalar dark matter candidate. And this actually can be detectable by atomic clocks because they're very precise. So let's come back to the example when I wrote down the Lagrangian for the Donahue and Damour dilatons. Let's say I write down I show only now the coupling to QED. Well, this coupling DE or dilaton E is going to enter changes of the fine structure constant, which are induced by the fluctuations of this dark matter candidate phi. And how you would basically, if you're an experimentalist, how you would proceed if you want to have bounds on DE is very simple. You measure clock frequency ratios. This is less noisy than if you measure single frequencies. And you measure a ratio between frequencies for two different atoms, essentially, or two different elements. It doesn't have to be atoms, it can be ions, etc. It just has to have some electronic clouds that you know the properties of. And so this ratio of clock frequency goes exactly proportional to the coupling, which makes sense, and has this K2 minus K1 times always kappa, which is gravity, and then this oscillating dark matter candidate phi of T. And so these K2 and K1 are sensitivities of specific elements to variations, of standard model parameters. Here, we're talking about the fine structure constant, so these would be more or less sensitive to variations of alpha. And so to take an example, a concrete example, in 2008, people have looked at this and computed bounds on DE based on ions of Hg is mercury and Al is aluminum. And so you can see that actually what you would do is you would take a reference element, which here is the aluminum ion, which actually depends in a very small amount on alpha variations. This is your reference. And then you would take something that hopefully depends very highly on alpha variations, here mercury ions, which has this sensitivity factor 3. And by doing this, you just measure what's on the left-hand side here, and then you would bound DE by doing this. Very good. So now what about nuclear clocks? Well, nuclear clocks are based on nuclear transitions rather than electronic transitions. So transitions of the nucleus. And I define here what an isomeric transition or nuclear transition is, which is simply an excited nucleon which relaxes and emits an electron. So actually, for most elements and most things, nuclear transitions are extremely high energy compared to anything that we can probe with lasers. These are this is the sea of blue dots that you see on top. All are out of reach. Almost all are out of reach, but one candidate is actually very well in reach of current laser technology, which is around basically between 1 and 10 eV. And this is a very special candidate. I mean, you can see that compared to all others for nuclear transitions, this is a very unnatural, you could call it unnatural point. And this is because there's a natural fine-tuning, a cancellation between the binding energy coming from the strong sector and the Coulomb force for thorium. So this is 229 thorium, TH is thorium. And essentially, these are the only candidates right now that we think can be used to make nuclear clocks. So as you can imagine, now we're going to again look at frequency oscillations due to the dark matter candidate. So again, they're parameterized as before by these dilaton-like couplings, some sensitivities, and the oscillating dark matter candidate. But now, because this is a nuclear transition, this has thorium has the power to be, has a very high sensitivity to nuclear and strong sector. Essentially, sometimes up to 10 to the 8 to 10 to the 10 more sensitive than atomic clocks used to be for the same sector. So this turns out that it's also a very high sensitivity factor for the variations of the fine structure constant, but this was already, at least in atomic clocks, there was a much higher sensitivity to alpha variations before. So the real impact that thorium might have on these experiments is that it's actually making a huge difference in the sensitivity to the strong sector. And I mean, the previous slide, I was showing sensitivity factors of maybe 3 for experiments in 2008. And here you can see this is 10 to the 5. This is because, again, the sensitivity factors are essentially proportional to 1 over the resonant frequency of thorium, which is actually very small. Very good. Okay, and based on various things I've seen in the literature, there's at least slides I've seen for different presentations for thorium clock presentations. In 2021, the 5-year plan was there was going to be prototype nuclear clocks, and dark matter searches would be in competition with current atomic and optical clocks. And the 10-year plan would be that there's an increase of more than 5 orders of magnitude in dark matter limits from clock experiments. So there's not yet a nuclear clock, but at least people have definitely made a lot of progress experimentally and have managed to excite exactly this transition, this nuclear transition in thorium atoms and ions. And finally, I show a plot of projected bounds because there's no clock yet. And I remind you of the interacting Lagrangian between the dark matter candidate and different, well, to abelian and non-abelian gauge fields. And here is a big plot with a lot of lines, so I will go through these lines one by one, but effectively this is a plot showing dg on the y-axis, so the gluonic dilaton coupling. The x-axis is the mass of the scalar dark matter candidate in electron volts, and the frequency is on the top, which is some unit manipulation and some factors of 2 pi essentially computed from the mass. Very good. So all this cyan zone are atomic and optical clocks, which are actually currently implemented. Now, anything that's red, orange, or purple are projected bounds on this DG coupling from thorium clocks based on the data that was taken from very recent 2024 papers of people that managed to excite this nuclear transition in thorium. Very good. Finally, the dark blue line is what people claim should be the bounds coming from a fully fledged single ion nuclear clock. So this is, I think, a very technical, for experimentalists, this is a very technical challenge, but if this is set up, this is the bounds that should come from this. Finally, you have a few gray regions, which are on the left, Milky Way, simply the existence of the current structures that we know in the Milky Way. There are bounds on dark matter from this. And then EP test is exactly what I was mentioning in the first or second slide, which is tests from equivalence principle violation. Very importantly, some of these experimental setups are so sensitive that they might probe couplings which are weaker than gravity, so essentially trans-Planckian scales. So this is very exciting. And for this reason, we need, as theorists, to make some types of prediction, and we try to make a first step in this direction. So we wrote down some truncation and we did some FRG computation. So now I come to this FRG computation. So it's a simple truncation with essentially a Euclidean gravity matter system with some scalar field, which is a massive ultralight scalar dark matter candidate, photons, and a dimension 5 interaction, a little bit structured in the same way that than these dilatonic couplings. But then you would tell me, okay, Gabriel, very good, but you just told me that thorium clocks are sensitive to nuclear properties. So why are you not coupling this to gluons also? Well, the point, first, I want to say what the main goal is of the work. And I come back to this question just now. So first, we know that this dimension 5 term breaks symmetries of the kinetic term for the scalar. So it breaks global shift symmetry and Z2 symmetries. So we actually expect that there's a fixed point at zero coupling, where the zeta coupling is essentially some sort of analog of the DE coupling, if you remember, from the dilatonic actions. And actually the main goal of the paper and what we achieved is that we wanted to study the relevancy of the dimension 5 operator, or the critical exponent, at the free fixed point. So yes, because this is helping us make predictions for this coupling. So now I come back to the question, why not couple it to gluons? Well, two reasons. Gravity is blind to internal symmetries, so it couples universally. And also the strong coupling is asymptotically free. So at the fixed point, if you're only interested in fixed point properties or fixed point relevancy of some operator, you can actually just compute this coupling zeta and this one operator, because non-abelian gauge fields will behave in an abelian way at the fixed point. So predictions for zeta, for this parameter zeta, are actually predictions for both dE and dG. So the abelian and non-abelian gauge couplings in the dilatonic picture. Very good. Then there's some, of course, technical things that one should be careful about. Of course, you need to gauge fix. So we choose Landau gauge fixing for the abelian gauge fields. And for the gravity, we have actually a very simple setup, which is Einstein-Hilbert action in Euclidean signature with a Landau gauge fixing and even Landau-David, where both alpha and beta are 0. As you know, Landau gauge fixing is useful because this is a fixed point of the RG parameters. Other than this, we will keep G and lambda as free parameters, and we will study what the relevancy is of this dimension 5 operator as a function of lambda star and G star, or potential fixed point values for this gravitational sector. Very good. Please interrupt me if you have any questions, by the way. Okay, so now something we all love, diagrammatic flows. You have 3 flows essentially to solve in this coupled system. A flow for the 2-point functions of the scalar field, the dark matter scalar field, of the gauge fields, and of this new dimension 5 operator, which has the dark matter candidate and the abelian gauge fields. So first, before studying this flow, I want to come back, take a step back, and mention that basically we will compare our results to a previous paper, which in 2021 considered a very similar truncation with axion-like particles, so pseudoscalars instead of scalar dark matter. So this pseudoscalar dark matter truncation essentially is written this way, where there's a crucial difference to our truncation. And the crucial difference is this operator is built with a fully antisymmetric Levi-Civita. What this means is that you cannot raise the indices of F mu nu or F rho sigma in any way, because any metric will be killed by the Levi-Civita. So what this means is that only these three triangle diagrams would contribute, because you cannot build any gravity vertices. And in our case, of course, you can, because there is no such Levi-Civita. And so in the end, one builds these extra diagrams based on 2 gauge, 1 scalar, 1 vertex, 1 graviton vertex, and also 2 gauge, 1 scalar, 2 graviton vertices. And so the question is, once we have these very similar setups, but crucial differences in how they enter at the level of the truncation, what is the effect of these extra diagrams on the relevancy at the free fixed point? Because both of these truncations are essentially dark matter motivated truncations with dimension 5 operators between a scalar or pseudoscalar and the gauge fields. So how will these new diagrams affect the relevancy is one of the main questions. So, okay, very quickly, what the actual setup is: we have regulators. They're adjusted to the tensor structures of the momenta in each propagators. I'm using a lithium shape function, and we're deriving analytic flows for the anomalous dimensions of the scalar and gauge field, of the dark matter mass, and of the zeta coupling. Again, I remind that the main goal is to study the relevancy of the dimension 5 operator at the free fixed point. So now I come to results. Very good. Okay, so now you have a plot with many things on it. So I will go step by step, but essentially the main point is that a positive critical exponent is relevant. So yes, so there's essentially 3 regions in this plot, which has as x-axis and y-axis values for the gravitational fixed point or potential fixed points of the gravity sector, which are kept as free parameters. And essentially 3 regions where either the mass is relevant and the dimension 5 operator is irrelevant, or the mass is irrelevant and the dimension 5 operator is relevant, or both are relevant at the same time, which is this cross region where the hashes are coming together into little crosses. Very good. Also, we have some type of coloring scheme, which is for a conformal mapping of the absolute values of the anomalous dimension for the gauge field, which is actually telling us, and so is this gray dotted line actually, or dashed line. Both of these are telling us where we trust our approximation. Because as you know, part of the approximation we're making in this is that we're only including a finite number of terms in the truncation, which are based on power counting, essentially. We're just going up to dimension 5 operators. And so we made a near perturbative assumption, and we would like the results reflect this and are still in a non-perturbative regime, near perturbative regime. So you might take bounds. You might want to bound the value of the anomalous dimensions to make them reasonable for in this parameter space. And actually, the scalar anomalous dimension gives you no bounds almost, because it's very reasonable in all of the plot. But the gauge anomalous dimension does get large in places, and this is why this line is useful. So why do I pick these 2 and -2. Well, 2 is because the dTRK in the flow will change sign when this anomalous dimension reaches above 2. And -2 is simply to mirror the +2. So this is what we define as the near perturbative region. This is quite a standard thing to do, and we trust essentially everything that is below this dashed line. So this dashed line is exactly the value where essentially the absolute value of the gauge anomalous dimension reaches 2, and so we want it to be below this. And below this, the dimension 5 operator is irrelevant. The boundary in this parameter space where it becomes relevant is actually quite far beyond the point where the anomalous dimension reaches above 2. And so we have some confidence that this operator is irrelevant. So now coming back to the 2021 computation for pseudoscalar dark matter, we also compare. Now we forget about the mass, but we made essentially the same plot where we compared the relevancy of the 2 dimension 5 operators, one with pseudoscalar dark matter, one with scalar dark matter, which is called alpha alp. So because of the structure actually of the coupling between the dark matter, the pseudoscalar dark matter and the gauge fields, the flow is actually very, very simple for the alp coupling, axion-like particle coupling. The flow is actually only coming from indirect contribution in a sense that it comes from anomalous dimensions of the gauge field and scalar field. And so there's no direct contributions. Whereas for us, for the flow that we computed, which is scalar dark matter rather than pseudoscalar dark matter, we do have these extra diagrams that I showed you on the flow slides. And we wanted to see what the difference was and what these direct contributions meant for the relevancy at the free fixed point. And what it means, you can see on the plot. So you can see that the region where the dimension 5 pseudoscalar dark matter operator is relevant, so where theta alpha alp is positive, is actually much larger than the region where the dimension 5 scalar dark matter operator is relevant. Much larger to the point where it even comes into the region where we trust that the gauge anomalous dimensions takes reasonable values. So it extends the regime of relevancy of this dimension 5 operator by quite a lot. And actually, you can compute the difference in critical exponents between the dimension 5 scalar and dimension 5 pseudoscalar. The expression might not tell you a lot because there's a lot of terms, but essentially, all direct contributions coming from diagrams will, for all positive G star, and until the cosmological constant is a fourth, will push the boundary towards irrelevancy. So in this case, this is, yes, the result we found is that in the scalar case, obviously this region where the dimension 5 operator is relevant is at much larger values of the gravity couplings, which might be a very non-perturbative effect that you, in principle, might not trust just based on the values of the gauge anomalous dimension there. Very good. So why do I say, I mean, this is a tiny technical comment on the side, but why do I care about 1/4? Because I know that I should care about 1/2, which is where I would get a singularity in the flow of the cosmological constant. And the reason is because this is where you can see this is where the gauge anomalous dimension changes sign. This is actually observed before for non-abelian gauge fields in 2011 and 2018. And in 2018, authors have found that actually this behavior disappears if you compute momentum dependence, because here we're in a derivative expansion to extract all flows. And so essentially we expect that this change of sign goes away. Very good. And so here I come to my conclusions and I read them off and leave them with you. But essentially, from the original idea in 2010 that scalar fields are inducing oscillating fundamental constants, people have found various ways of experimentally testing that to very high accuracies through atomic and optical atomic clocks. And this is actually a way of detecting scalar dark matter. I mean, the original idea of oscillating fundamental constants to a scalar field is not really about dark matter, but this can be very efficiently applied to detect dark matter. Again, these atomic clocks are very precise, but in the future, nuclear clocks will take over for the strong sector because they offer huge sensitivity improvements. So much better bounds by sometimes enormous numbers of orders of magnitude. And some of these bounds might even be trans-Planckian. So these experimental setups are very sensitive. On the theoretical side, we thought this was a very interesting idea, so that one needed to make predictions. And the prediction we made is that the contact scalar dark matter interaction with photons and gluons is not generated by quantum gravity fluctuations, just because the fixed point is at 0, and that at this 0 fixed point, we found that this operator is irrelevant. So this essentially the coupling can be set to 0 at all scales, and this is the prediction that we make, is that dE and dG can be 0 at all scales. And this is a testable prediction. And finally, we made some comments on comparing this between scalar dark matter candidates and pseudo-scalar dark matter candidates. Especially, we compared the relevancy of these dimension 5 operators at the free fixed point, and we found that actually, in the case of the scalar dark matter candidates, there's direct contributions coming from diagrams that generically push these dimension 5 operators towards irrelevancy. So it's even harder to make them relevant with quantum gravity fluctuations. And that's it for me. Thank you very much.
Thanks, Gabriel, for the nice talk.